So hi everyone, it's Ophir here. I'm like to introduce Dr. Ron Caplan, a computational scientist at Predictive Science Inc. Ron will introduce us to POT3D application, one of the main lead developers. Ron, go ahead.
Oh, can everyone hear me okay?
Yeah.
Okay, cool. Okay, and everyone can see this okay? Yeah, everyone sees the presentation?
Yeah, we can see it.
Okay, great. So I'm Ron Caplan, computational scientist at Predictive Science Incorporated. We're a small company in San Diego that does basically science research, mostly in the field of solar physics, but also in mathematical epidemiology. So we were asked to provide our application for the student cluster competition called POT3D. So I'm just going to go over the code, how it's used in industry, what the model does, what the code actually does, what it computes, how it does it, and its parallelism and performance. And then we'll quickly go over the task for the cluster competition, and then I have the links to the cluster usage tutorials, and I'll talk a little bit about tuning options that you might want to do while you're playing with the code. So POT3D, it's a code that computes approximations of the solar coronal magnetic field of the sun, which we call potential fields, and it uses observations of the solar surface magnetic field as a lower boundary condition. So it's a 3D spherical solution, 3-component magnetic field. It's parallelized for CPUs and GPUs using MPI and OpenACC, as well as standard parallelism, which will be do concurrent. And we use HDF5 for input and output files. So POT3D is also included in the spec HPC benchmark suite for 2021. That version actually has OpenMP target offload included in it, but that's not the version you guys are using. And the current release, which is the one you'll be using, is on GitHub at that address, which you probably already have. And if you want to read some publications on the use of the code, there's these two references here. The variations of finite difference potential fields has a section on the code itself, but then also uses it for a study of variations in the solutions it produces. And the other reference there more talks about the adding OpenACC to the code back in 2017. So when POT3D is used in industry, so those approximations to the solar coronal magnetic field, they're used widely in our research. They're very inexpensive to compute at moderate resolutions compared to a full magnetohydrodynamic model of the solar corona, but it can still provide a pretty good approximation to the fields. So those solutions are also used as initial conditions for our large MHD codes. So for the magnetohydrodynamic codes, you have to start with some kind of field in 3D. You can't just start with 0. And so we actually solve the potential field as an initial condition for that field. So that's
Ron, yeah. Quick question here. Are you moving the slides? Because we see only the first slide.
Oh, really?
Yeah, we see we have 2 windows. Yeah, now we see the second slide.
Hold on, let me try this again. Let me just share the screen.
Share the other screen.
Do you see it now?
Yeah, now we see the full. Move to the second slide. Okay, now I see the second slide.
Good.
Yeah.
Okay. So this is everything I said. We're here. All right. So you can see this page now, usage in industry.
Yeah, we see this.
Yes, thank you.
Okay, cool. So yeah, so besides using as initial conditions for large magnetohydrodynamic simulations, so the potential fields themselves are used a lot. There's something called the Wang-Shili WSA empirical solar wind model. So when you want to sort of estimate what the solar wind is like at the outer edge of the inner heliosphere and into outer edge of the inner corona, and you want to project that back to Earth for space weather applications. So a lot of people use magnetohydrodynamic heliospheric simulations, which are much faster than coronal ones for reasons I won't get into. And so to use those, you need a boundary condition of the solar wind. And the coronal MHD solutions are not fantastic at getting the solar wind right. So they've created empirical models based upon the magnetic field at a certain radius between the sun and Earth. And one of those models is called WSA. So for the WSA model, you create a potential, actually two potential fields that are connected, and then you use that field to create your solar wind temperature, velocity, and density. So there's a software that we have called CoreHel, and that's hosted at NASA's Community Coordinated Modeling Center. And POT3D is the code that's used to create those potential fields for that WSA model. It's also going to be used in an upcoming open source space weather modeling package. There's a program called SWQU, which is the next generation software for data-driven models of space weather with quantified uncertainties. And in this program, we're going to be using POT3D as the potential field for this WSA model, which will then go to a much higher order fancy cube sphere heliospheric code. And so POT3D is a big part of that project as well. Okay, so like I said before, potential fields are much more inexpensive to compute than full MHD solutions. But because they're so easy to compute, it opens the door to computing them at very high resolutions, much higher than you could do MHD. And so once you go to these high resolutions, the solution becomes much more computationally expensive, requiring a high performance code. So POT3D is able to perform at that level. There are other potential field solvers out there, but they're mainly for lower resolution applications. So in the paper that I referenced before, we did the largest ever potential field solution that we know of, which consists of 6.6 billion grid points. What you're looking at here is a composite of some diagnostics called a QMAP and the magnetic field itself, and what's called a coronal hole map, which is tracing field lines through the resulting field and doing some analysis on them and coloring them accordingly. And you just see the immense amount of detail out of 6.6 billion points. So even this simple, quote unquote, simple potential field model is actually can bring out lots of complexity for large resolutions. So just a quick background of what is this model. So if you have Maxwell's equations, which just says the curl of a magnetic field is equal to the current. So if you assume that there's no current, which is a valid approximation in many parts of the lower corona, then you just get the curl of B as 0. So if you say that the solution we want to be in the form of the gradient of a scalar potential phi here, then, and we also have a divergence-free condition, which is that there are no magnetic monopoles, so that the divergence would be a 0. You combine those two together and you get a Laplace equation for the scalar phi. That's the equation that POT3D solves. So for boundary conditions, at the lower boundary condition, we have the observed radial magnetic field from observations that we use. And then at the outer boundary, we have two choices in the code, but typically we'll use the source surface where you have the field fully open at the outer boundary, basically the straight lines. And then with it's periodic, of course, in the phi direction around the sun. And then the poles are just done with polar averages. Okay, so how do we solve this in POT3D? So we use a non-uniform logically rectangular spherical grid. And an example of that grid is over here. So basically we can modify the grid resolution in theta or phi to sort of highlight a high detailed area, like you see this little blob in the middle. But it's still logically rectangular. We're still on a r theta, a theta phi, r theta phi grid. And so that allows it to be much more simple to analyze afterwards instead of something like AMR. So to solve this, we represent this Laplacian as a matrix vector product. And to do that, we use a second order finite difference. And then the coefficients for the local stencils are stored in a sparse 7-banded matrix in what we call a modified DIA storage format. So if you look at on the right-hand side, this is sort of how the matrix vector product is computed. This is just a 2D example, but in POT3D, it's 3D. And so the matrix looks similar to the matrix down below. So it's a banded matrix, and we just store those diagonal bands in a rectangular array. And that's what the DIA storage format is. And we solve this using an iterative preconditioned conjugate gradient solver. And that basically just consists of a bunch of AX plus BY, some SAXB, well, it's DAXB, I guess, it's double precision, but and matrix vector products, and there's dot products involved. And so this is somewhat similar to like a stream benchmark in terms of the core computations, but the spherical grid adds extra things like the polar boundary conditions and things like that. So the logical grid of our TP is broken up into 3D blocks, and it's split as evenly as possible across the number of MPI ranks that you're going to use. And for things that require neighbors, like the matrix vector products, we use the asynchronous point-to-point MPI communication, like I send and I receive. We call that CMean in the code. And for dot products and other collectives, we just use all gathers to do the dot products. The 3D domain is done using the Cartesian create in MPI, so it allows for reordering of the ranks depending on your network topology, although in my experience, I've never actually seen the MPI library reorder the ranks. So it's, I'm not sure if that's actually doing anything, but that's something you can play with. Each rank computes its sub block of points. So there's different ways to run the code in that way. So one is MPI only. So this is what you would use on the CPU. And it basically uses one CPU thread per block, per rank. And so that would be where you're running on, thousands of MPI ranks across thousands of cores. Each rank would just compute its own small subblock, as shown over there. And then the other way to run the code on GPUs for multi-GPUs is where each rank is computed on one GPU. So in this situation, you would, if let's say you're running on 4 GPUs, you would only use 4 MPI ranks, unless you wanted to oversubscribe the GPUs, but that's a whole other complicated thing. And you have to make sure that that's enabled. And it's not clear that that's going to get you much. But typically, you use 1 rank per 1 GPU. The other way to run the code, because it uses Fortran standard parallelism of do concurrent and OpenACC, you can actually compile the code with the NVIDIA compiler on the CPU for multi-core parallelism, which uses OMP num threads and ACC num core environment variables. And you could then run it in a hybrid mode. So each MPI rank, for example, could be on each socket, and then each socket could be threaded for the cores on the socket. In my experience, I haven't found this to actually increase the performance of the code. However, there was a paper on the Spec HPC benchmark, which has POT3D in it, and they actually found that for very, very large numbers of cores on a supercomputer, you can actually get better results in this hybrid mode. So that's something you might want to play with that we'll talk about later. And then the parallelism on each block is done through the use of using do concurrent where possible, shown on the right here. And then OpenACC for loops that don't support do concurrent yet, parallelism. And also OpenACC is used for manual data management between the GPU and CPU. So when you run it on just the CPU, all the OpenACC data managements are ignored. And examples of some loops are on the right here. Okay, so let's talk about performance a little bit. So it scales very well to many MPI ranks on both CPUs and GPUs. And the plot I'm showing here is the data that was released from this paper by Brunst et al., where they took the Spec HPC benchmark and ran it on a bunch of computers in different ways. And this is the Spec small test. And by small, it's 300 billion points, so it's not very small. And what you see here is they made their data available for their paper, and so I replotted it just for POT3D here. And the spec score that you see on the y-axis, that's how many times faster it is than the reference run in the spec benchmark. And the spec reference run is that black diamond, and that's running on 10 nodes of, I believe, a dual Haswell CPU. So what you see is that obviously the GPUs are, very, very fast. The solid and dashed lines are whether it's using, I believe, OpenACC versus OMP target offload. The red lines is actually an AMD GPU, but I don't think you'll be using those. And so you see on the CPU, you get almost perfect scaling all the way, here out to 64 nodes. And on the GPU, the scaling starts to taper after a while, but overall, running on 2 nodes is like the equivalent of running on like 40 nodes of the CPU in this case. And this was with Frontera. So let's keep going. So one of the reasons why GPUs work so well in this code is because POT3D is very highly memory bandwidth bound. So here's another figure from that same paper showing the arithmetic intensity, or the flops per byte, of the different benchmarks inside the spec HPC suite. And you see that POT3D is right on that blue line, way down in the bottom left corner. That implies that it's incredibly memory bandwidth bound. On the right, what I'm showing there is my own runs of the spec HPC POT3D tiny test, which is a smaller test that'll fit on a single GPU. And you see that I'm plotting the peak memory bandwidth of the system or GPU versus the spec score. And you can see it correlates extremely well. So the more memory bandwidth you have, the faster the code's going to run. Here, for example, my RTX 3090 Ti is, many times faster than, a single socket EPYC in this case. So now let's talk about the cluster composition task. So the test problem you're going to be doing is called ISC23. And this test is derived from the small test in the spec HPC benchmark. It's basically the same test, just copied over. I think the input might be slightly modified, but basically it's the same test. And the reference timing, just for, just to compare to, is running on, if you run this on 10 nodes of a dual socket Haswell supercomputer with 240 cores, then it takes about 1600 seconds. And that many nodes of that CPU is equivalent to 680 gigabytes per second of memory bandwidth. So whatever memory bandwidth you are running on, you can compare it to that and sort of estimate what your performance should be. And in the GitHub repository, this test is in the test suite folder called ISC2023. And that's where the inputs are for this. It's basically about 300 million points. This is the picture you're seeing here is the lower, is the solar surface radial magnetic field, which is the boundary condition of the input. And this takes about 25,000 solver iterations to complete. Okay, so this I took from the Wikipedia that you have the link to. So for the task, and basically, like we said before, the input's under the ISC2023 folder in the test suite. And the task is to run this on both Bridges 2 and the Fritz supercomputers using 4 nodes. And you can experiment with the number of ranks per socket and NUMA domains, and I'll talk about that a little bit more detail soon. And it should converge with the 25,000 iterations, and it'll print out something like you see here. The actual residual that you're going to get is going to vary because the dot products are not reproducible because they're out of order for the MPI collectives. And also on GPU, you're going to have obviously floating point variations. So basically, it should be similar to that though. So the task is to first profile a run. So use any of the clusters to do an MPI profile using the 4 nodes. And then you're going to want to submit that profile. And then you're going to indicate the 3 main MPI calls that are being used, the runtimes, and the total MPI time for the test. The code has timers in it including some MPI timers. However, we define communication time as not just the time inside the MPI calls, but we also include loading and unloading of buffers. And also the dot products act as synchronization points. So any load imbalance of the computation tends to show up in the time around the dot products. So with your profiler, you'll actually be profiling the actual MPI calls. And so you should see this small, any load imbalance, which there always is, you should be able to tease that out from the actual dot product calls themselves. And then for your bonus task is to run this on the Bridges 2 cluster using the V100 GPUs. And in this case, you're going to use 4 GPUs, and it's recommended to use 1 MPI rank per GPU. So I believe that's 2 per socket. And then in order to do that, you're going to have to use the NV Fortran compiler. And the HDF5 IO library needs to be built with the same compiler as the code that you're going to compile the code. There is a way, I think, to compile just the module part of it, but basically you're going to want the HDF5 library compiled. So if you grab the version 1.8.21, you can just install that from source and then, put those paths in your LD library path and compile linking to those paths, and it should work fine. An example build script for the NVIDIA compiler is inside the GitHub and the build examples, build GPU NV22.3 Ubuntu 2004. I'm pretty sure the supercomputers OSs are not Ubuntu. They're probably some kind of variety of CentOS or Rocky Linux or something like that. So there might be slight differences there. And actually on Bridges 2, there's an issue with LTIRPC, but I don't think that's for HDF5. So you should be fine with that one. There is an option in that build script to enable the cuSparse library linking. cuSparse is a NVIDIA-made sparse matrix compute library, which includes an ILU decomposition, which is one of the options of the code that we're not using. And therefore, if that linking of cuSparse library is causing problems, just turn that off by setting that environment to 0 inside the build script. We decided not to go with the other version, the other preconditioning option, because that. So I think we consider it cheating if you use that, because it will go twice as fast if you use that. But because it's too complicated to deal with, basically we turn that off. So the input file that's in the test suite of ISC 2023, you won't be modifying the preconditioner option in there. I mean, you can on your own time just to see what it does, but for now we're leaving that to 1. And then you're going to submit all your build scripts, run scripts, inputs, and output text files, but not the 3D output files. Okay, so for the cluster usage, I'll just refer to these links, which are on the Wikipedia. There's too much there to reproduce here. I personally have used Bridges 2 in the past, so I'm familiar with that. If you're having problems with that, you can contact me. I have not used Fritz, so and then okay, so what can you do to play with this code in terms of trying to get better performance than your competitors? So just to review, like I said before, every MPI rank computes a local block of grid points. So in MPI only mode, that means that each one CPU thread is computing its local block. So you're going to want blocks that are small and lots of CPU threads. In GPU mode, you're going to typically have one GPU compute the local block. So the local blocks will be bigger, but they'll be computed on the GPU. And I have the compiler flags here that you would use for the NV compiler. And then for hybrid CPU mode, I put those compiler flags here. And like I said, it will use OpenMP threads and ACC dumb cores to define how many threads. So almost always, like I said, on CPUs, running an MPI only mode is going to give you the best performance. So that's the most simple way. So it's no special flags. It's just you run it, for as many ranks as you have. However, I should note there, and I'll mention it a little bit later, that even in MPI only mode, depending on your system, you might not want to use all the cores available on each node. So for example, on the AMD EPYC CPUs on Bridges 2, we find that for when we're using many nodes, we get better performance if we use less cores per node, and that's because of memory bandwidth saturation. So you're going to be only using 4 nodes, I believe, so you might not notice a difference, but you can play with that. So for very large numbers of CPUs, like I said, running hybrid at CPU mode can be faster. But getting the right thread, node, socket, core affinity, and the log script and the environment can be difficult. And I believe you're only running on 4 nodes. So I highly doubt this is going to be faster. However, you know, I haven't gone into that, especially with the newer EPYC CPUs. I have not tried this. So you are free to experiment with that. And to do so, for the EPYC CPUs, they have 4 NUMA domains, and I believe they are set up. Like you can set up those processors to in the BIOS to be 1, 2, or 4 NUMA domains, and I believe they're set up for 4. And therefore, you know, getting the affinity right for threading is a little bit tricky because you're going to want to make sure the first touch policy of allocating of setting arrays is done on the threading level at the correct affinity of, you know, probably 1 MPI rank per NUMA domain, and then threading along that, or possibly just 1 rank per socket, or even 1 rank per node and threading along that. So that can take you down a rabbit hole. So I would suggest MPI only to start. And then if you want to play with the hybrid mode to try to squeeze out some more performance, then go for it. And then even in MPI only mode, I would test around with the number of MPI ranks per node you use, and, you know, and vary that. For the on-site cluster competition, where I guess you guys are bringing your own hardware, as far as I know, like I said before, maximum memory bandwidth is going to determine the performance of this code. And so you're gonna get much better performance if you bring a bunch of GPUs with you versus CPUs. That's for sure. And the GPUs you bring, the more memory bandwidth they have, the better. And so you just have to be careful that, you know, I wouldn't bring low-end GPUs that have very little RAM, because then the problem might not fit on them. So you have to keep in mind the RAM of the GPUs versus the memory that the test you're doing takes. But definitely, if you want to get the best timings on site, I would bring NVIDIA GPUs. And that's all I have here. So I'm open for questions. Oh, I should check the chat.
Have any questions, just go ahead and shout them. Don't have to shout, but I can talk. And in any case, we have the Slack channel. If you have later on questions, any issue related to that, feel free to contact us, either in the group channel or in the main channel. We'll try to address it. Okay, looks like everything is really, really easy, and no other questions.
Okay.
which is good for us. But we are, you know, we have some
we do have a
question.
Can we change the ifprec parameter in the input? So that's that preconditioner I was talking about. So for the official student cluster competition rules, as far as I know, you're not supposed to change that. You're supposed to leave it at 1. If you want to play with it yourself, if you set it to 2 on the CPU, it'll do an ILU0 decomposition. On the CPU, that can result in a performance that's 4 times faster, but it uses more RAM. So you have to make sure that you can fit it on whatever number of CPUs you're using. On the GPU, if preg equals 2 will only work if you compile linked to the cuSparse library, and that'll provide a 2x performance benefit versus running the GPU if preg 1. However, it's up to the organizers to determine whether you're allowed to play with that or not. And we sort of decided to not have that be part of this because it gets a little too complicated. So, but you know, I'm not in charge and I'm not a judge, so it's so for now I would leave that at 1. If you've done everything else and you want to play with it, then you can set it to 2. But I don't know about for the official results, you probably have to leave it at 1, as far as I know.
But I suggest currently is leave it at 1. Well, let's talk about that offline, and if we have any feedback, we'll update you. Can we change the Fortran code?
So that's for you to determine, I guess.
For my side, I would say first submit the results as is. If you have any code suggestions, fixes, or improvements to the code, you can do that and send that as well, and send also a small README file or something that shows what was done and how you managed to improve the code. And also you can submit it as a pull request in the Git if that helps the code. If the code is not some places can be written differently to improve the code, and of course not to change the results or not to change the problem. That's possible.
Yeah, I mean, if you wanna write your own multi-grid solver in there to make it faster, feel free to send that to me. But okay, looks like there'll be questions sent later.
Okay.
Wait a little bit because sometimes it takes people time to type.
Yeah. No here at all.
Yeah, and if you have trouble with the HDF5 library compiling it with the NVIDIA compiler, you can send me a question on that. You know, we have our own script to install that and whatever flags we use, and I can sort of put that in there to how to activate that library. It might be on the system, possibly, you know, in the GPU module or whatever. I know that in the past, some people have had problems with too new of a version of HDF5 with this code, but you know, you can try, if there's already one available, then try it out for sure before compiling from source. But
I have another feedback for the PC cluster. Last year we had a hard time to get allocations on the GPU cluster. They have, I think, 6 DGXs or 8, something like that, with V100, and normally it's being used by many people. If you feel you don't get enough, we got the resource tokens, let's call it. But if you feel you don't get enough time or not a reasonable amount of time, let me know. We can try to expedite that. We have, and another feedback that we have 2 months. So let's see, try to use the amount of time, the whole 2 months. Last year, most teams, they waited 1.5 months and then tried to work only on the last 2 weeks, as all the students tried to do the task towards the end of the time. And then there was a lot of stress on the amount of jobs and requests on the clusters. We were trying to give you 2 months on the clusters, so we'll have enough time to get allocations and work and try different things within these 2 months. If you have difficulties one day, the next day is free, maybe on the night is free. Work on different hours and see what you try to enjoy and learn and use the most out of it.
One other thing, the test you guys are doing, which is the ISC23, is that 300 million point large test. In the POT3D GitHub, there's an examples folder, and there's also the other test suites in there. There's much smaller ones there. You can use those to just practice compiling and running the code on your own machine. So this code has been tested to compile and work on Mac using Mac ports. It also will work on any Linux machine you have, and it'll even work on a Windows machine if you have the Windows subsystem for Linux Ubuntu installed. So if you have like an NVIDIA gaming GPU, for example, you can have WSL run and compile this and play with it and get it running on your own desktop before you use up the cluster. So even the smallest test, even just on your normal laptop, you could install this and test it out first. So you might want to do that just to get familiar with it before having to submit jobs on the cluster for the large test.
So to reply to one of the questions on the GPUs, we have them only on the PSC cluster. And again, this resource is from last year experience, was fairly busy. So again, try to, if you plan to do the GPU test, it's more complicated. That's why we put it as a bonus task. I mean, if you finish, let's say you finish the CPU task, and you can move on to the GPU task if you have time, and then try it out.
I posted the slides from this talk on the Slack as well.
Great. Any additional questions, everyone? Okay, so Ron, we'd like to thank you. It was a really great presentation. Everything is nice, explained, and you are a good trainer and tutor. If we may have additional questions later on the Slack or emails, I try to move everyone to Slack. We have all the teams there, so all our announcements will be there. Any issues, any hard times you get, don't leave it alone. Let us know. We'll try to help you with debugging whatever you have. We are here for you. Hope you learn, take it to your next step and help you with your career. And again, I would like to thank Ron. I will add the recordings later on. I will send you a link, and we'll continue discussions via Slack. Okay.
Have a good day, everybody.
Okay. Bye, everyone.
Thank you. Bye.
Bye. Thank you.